Okay, relative motion. What is relative motion? It's kind of an idea, and the idea is that when you're talking about something moving, or something, or lots of things moving, it depends. Their motion depends on how you look at it. Just as an example, if you're in a car driving along at, let's say you've got a couple people in a car, and this is a horrible car, but say you got a couple people in a car and they're driving along at 60 miles per hour. That's not something that they would argue about, but how fast are they going compared to each other? If they wanted to, you wanted to hand someone a pencil or something, you just hand it to them, and compared to them, your speed is 0 miles per hour because you're in the car moving together. Now, compared to other stuff, like a mailbox sitting on the side of the road, then the mailbox looks to you like you're sitting still, and the mailbox looks like it's coming at you at 60 miles per hour. I hope that makes some sense to you. And now that you've suffered through my horrible drawings, let me put one up here that I got off of the internet. And let's say, whoops, not that small. Let's say that this person is going toward the right, and over here, this person is driving toward the left. So we're going to give these guys some vectors here. We're going to say this guy is going 50 miles per hour to the right. That's what that arrow shows. And let's say this guy is going to the left at 60 miles per hour. So let's say, no, they're not going to collide, but let's say that they're going to drive past each other, and they're going to high-five each other out the window as they go by. And if they do that, how fast do their hands hit each other? Well, think about that for a second. Maybe pause the video. So this person's going to the right at 50. This other person's going to the left at 60, and they're going to high-five each other. In this case, what would happen is, to figure out the velocity where their hands meet, you would add them together. So when they high-five each other, their hands are going to hit each other at 110 miles per hour. So yes, they probably are going to get hurt. Okay? Okay, I've switched things around a little bit here. We're going to say that this person's velocity vector is, I don't know, 60 miles per hour to the right. And we're going to say that this person's velocity vector is 55 miles per hour to the right. So since we know that your motion depends on the observer, what are these two people going to say about what each other are doing? Are they going to say they're even going in the same direction? That's kind of what we're thinking about here. So let's say this guy in this car right here, let's say he looks back in his rearview mirror and he sees this guy catching up to him. Well, how fast does it look like he's going? This guy sees the guy in the red car catching up to him rather slowly. So what you would do in this case is you would go 60 minus 55, and you'd get 5 miles per hour to the right. So this person in this car says this person in this car is going to the right at 5. And it's a positive number because they're both going in the same direction. Kind of an assumption that I made here was that positive was to the right and negative is to the left. Okay, so what about the person in the red car? What would he say about what's the other car's motion? Well, if you ask this guy, the guy in the red car, how fast the guy in the blue car is going, well, the guy in the red car is catching up to the blue car. So if the guy in the red car were to be considered sitting still, he would see the guy in the blue car going backwards. He's coming toward him. Even though they're both moving to the right, it's this guy's point of view that the guy in the blue car is going to the left. So in this case, it looks to the guy in the red car, it looks like the guy in the blue car is going negative 5 miles per hour. And in this case, what the negative means that the negative means that it looks like he's going to the left. So the guy in the red car thinks the guy in the blue car is actually going left. These are potentially tricky problems, but if you take a minute and think about what each person's point of view is, it's relative to each person. If you think about that for a minute, these problems get a lot easier. Okay, I want to spend just a little bit more time talking about one more problem. Let's say that we've got a river, and this river is flowing down to the left here at 2 miles per hour, and we've got a person who is capable of swimming at 3 miles per hour. So if this guy hops in, he can go 3 miles per hour. Well, how long would it take him to go I don't know, let's say a distance of 10 miles, that's a long time, I know, but 10 miles downstream, or how long would it take him to go 10 miles upstream? So a distance of 10 miles upstream. So if we wanted to figure these two problems out, what speed would we use? Would we use 3 miles per hour? The answer is no. We've got to think just a little bit more. We know that time equals distance over speed. So no matter what, for either of these problems, we're going to have our 10 miles on top. But what speed, or in this case velocity, what velocity would we use going downstream? Well, if the person hops in the water and goes downstream, then you're going to have the river plus the person's speed. So it's actually going to be 5. So if he goes downstream, his speed is going to be 5 miles per hour. So that's actually going to take 2 hours to go 10 miles downstream. But what if the person goes upstream? Well, here the river and the person are working against each other. So in this case, if he can swim at 3 and the river goes at 2, his actual speed is not 5 miles per hour. It's actually 1 mile per hour. So our distance here is 10 miles divided by 1 mile per hour. So the miles cancel. So if he goes upstream and he wants to go 10 miles, it's going to take him 10 hours. So that's another example of how the motion depends on what you compare something to.